Okay, due to these limitations, okay, we continue this technique explanation of the geophysical techniques. Due to the limitation of the conventional technique using borehole, then we can propose to use another technique, combine this technique, which is using this geophysical method, correct? And then this geophysical technique is advanced, quite already advanced in the oil explorations to get the model of the grounds to find where is the oil field. So just imagine how they in the oil industry they try to find where is the oil even underwater. So this is a technique is very powerful. So now we are one use this technique in the civil engineering works. So this technique advantage because it's non-disruptive, non-invasive, not touch the ground. Some of that not touch the ground, and relatively speed is quite just very quick test. So this geophysical technique can divide it into a few techniques. We call that seismic refraction. Both is seismic. Some we use seismic refraction or refract and reflect. We have resistivity, electrical resistivity. They call it electrical resistivity technique. Then we have ground penetrating radar, GPR, and then we can discuss gravity. So now we have to go to this seismic refraction. Okay, for seismic refraction, this is a technique that very common used in the civil engineering work for to detect the boundaries between soil and rocks, and also to get the soil profile, to know where is the hard layer or soft layer. So for the seismic refraction, measurements are made by measuring the time travels of refracted seismic wave as it travels from the surface through one layer to another and is refracted back to the surface where it's picked up by geophone. So I will show you how in animations that shows this how this wave propagate in the soil and refract to the surface of the ground. Okay, and then the sensor, we call it geophone, able to pick up the vibrations from the seismic wave. Then we show you the impact. Impact means the source of the seismic that we produce. Okay, and then the wave speed, the speed of wave is related to this density, hardness of material, or call that stiffness of material. Okay, so mean that if we have very dense material, our speed is very high compared to low density. Okay, and then we can able to determine density, and then the velocity can be utilized to determine the material. So we have a table of velocity that we can use to interpret type of material. Okay. This is the equipment that we use in seismic study, which is involve the data acquisitions. We call it teralogs. Then we use seismic cables. Then we have a trigger cable. This is trigger cable. Then we have a sledgehammer. This is where we hit this ground on top of this sledgehammer. For this is a strike plate. So we use that sledgehammer to hit that strike plate on the ground. So we use battery, external battery, Then this is geophone. Then this geophone is sensor that able to measure any vibrations on the ground. Well, yeah. So this is how they put the arrangement of the equipment on the field. 1, 2, 3, 4 up to 24 is the geophone. Our geophone here. So this is our equipment normally put in the center. So we have hammer shot here. So this is hammer. So the hammer is used the cable, trigger cable. Then the printer, we don't need to bring it on the field. We can use in the side in the office. So we have a few spot for to have this seismic data, which is normally we do about 7, sometimes 5, sometimes we can do 9. It depends. But normally they use 7 short point. But if you increase the numbers of short point, so your data much you can get better data, but takes longer time to do this testing. This is where we call it short point. To this we can show you what is the short point means. Okay, this is the cable. Then we have this is geophone, and this is how they see. This is hammer, this strike plate. They hit this hammer on the strike plate to produce the seismic wave. And what you can see here, this is a center, the ABEM. So the operator, so when they hit this ground, all the workers must be stand still, must still at their place. So meaning that we just hit the ground, the vibration that produced in this ground is on that area only. It's come from this source on that area. So the sensor here you can see here. So these are you can see here like this. So mean here this is time. This is you can see 1, 2, 3 here up to 24. These are numbers of geophone. What you can see here when this wave break here means this is the when we wave arrive at the geophone, so they trigger this wave. Okay, this here wave still not reach on that geophone. So if like this, so they strike on here our source here, so that travel through this point and through this point. Okay, center of it. So they have a few short point, maybe here, maybe somewhere here, somewhere here, somewhere here, and somewhere here. They have normally they have 7, 2, 4, 5, another here, quite far from here, so can be like that. There is an example of these seismic works. Okay, look on that. Look on this monitor. You can see the data come up. Okay, and there. Okay, see this vibration. Okay, they do a few times to stack this data to remove the noise, so they are averaging all this data. You can see here they do normally sometimes up to 60 blows to get this good data. So this is how we do this strike hammer to produce the seismic wave. So that seismic wave will propagate through this under the subsurface and then reflected to the surface if we have different density. Some of that will be refract. If you here, you refract here. If at certain angle, that the wave will be refract at 90 degrees, which is along these boundaries of layer 1 and layer 2. Yeah. This case is layer 1 must be layer 2 more dense than the layer 1. That case. So here velocity of V2 is higher than V1. This case will be happen. Okay, how this looks like. So look on that videos.
Seismic waves travel at different speeds through different materials. In this two-layer model, two wave fronts leave an impact at the same time, but the lower layer is faster. When an explosion or impact occurs at or near the surface, waves travel away in all directions. In a uniform medium, they would travel straight paths away from the source. But what happens if they hit a boundary between faster and slower layers? Waves react at the boundary according to Snell's law, such that when energy arrives at a boundary, some of the energy is refracted in the lower layer to speed up or slow down depending on the media. At the critical angle, waves are refracted 90 degrees and travel along the boundary in the fast layer. Ray paths aimed at the layer at more than a critical angle will have all the energy reflected back to the surface. This is known as supercritical angle. Rays that strike the boundary at less than critical angle, subcritical, have most of the energy refracted to travel at a shallower angle in the fast layer with less energy reflected upward. The critical angle marks the angle where the wave is refracted parallel to the boundary and travels along the upper surface of the fast layer while sending a series of rays known collectively as a head wave back to the surface at the angle of the initial direct wave. When we look at all the waves, we see that the wave traveling along the critical wave path can actually reach a point before a direct wave traveling a shorter path in the slower layer.